Wrapping up the sensory system is the last part. We're going to go over the ear, taste, and smell. And so first, anatomy review again. You want the full review, YouTube, anatomy playlist. Chapter 18. The ear, like the eye, you have an external, middle, inner ear. Again, super quick review. You guys hopefully remember your anatomy. You have the external acoustic meatus. That's in the external ear and the auricle. It's going to basically funnel sound waves. So like light waves, sound also is wave energy. And those sound waves are going to be funneled through the external acoustic meatus, and they are going to hit the tympanic membrane. Tympanic membrane separates the external ear from the middle ear. And we call it the eardrum because these waves hit this opaque translucent membrane that's sealing off the external air from the middle ear, and it's going to vibrate that tympanic membrane, which is also attached to the auditory ossicles, which are these small little bones, and that vibration energy is going to be transmitted from bone to bone to bone. And you have the incus, the malleus, and the stapes, three little bones, and they are transmitting this vibratory energy in the middle ear. The middle ear is called the tympanic cavity, and it is open to the nasopharynx. And this is because you want atmospheric air pressure to be the same here. So air pressure should be equal to air pressure in the external acoustic meatus. And this allows the tympanic membrane to vibrate appropriately, and then the auditory ossicles to vibrate appropriately. So that's why when you go up in altitude, you generally yawn or increase or open your nasopharynx to get that new atmospheric air into your tympanic cavity. It's because there's less pressure in air up high. So that's the nasopharynx, and it's connected with the structure called the auditory tube, or what has been called the eustachian tube. The eustachian tube equalizes the pressure in the middle ear. That vibratory energy is then transferred into the cochlea. The cochlea has the little hair receptors for hearing. You also, in your inner ear, have the semicircular canals, and these have the receptors for rotational movements. You also have the vestibule, which is the utricle and saccule. Sorry about that. And these have the receptors for gravity and linear acceleration. So you have receptors for rotational movements, gravity, linear acceleration. So that's your balance and equilibrium. And then you also have the receptors for hearing in the cochlea in the inner ear. So tympanic membrane, your eardrum, is the boundary between the external and middle ear. It's connective tissue that vibrates in response to sound waves. And it's going to turn sound wave energy into vibratory energy. It's an energy transducer. And so that's that transferring sound energy to the bones in the middle ear. It's transferring wave or sound wave energy to the vibrations of the bones of the middle ear. These little auditory ossicles, they're small little bones, the malleus, incus, and stapes. They're suspended by ligaments and joined by synovial joints. They're tiny little synovial joints, and they transmit the vibratory energy from the eardrum or tympanic membrane to the oval window of the cochlea. There's the tensor tympani and the stapedius muscle that contract reflexively in response to loud sounds. This is to prevent that vibratory energy being too high, because then there'll be too much energy transferred to the oval window of the cochlea. So that's what those little muscles are for. In the inner ear, again, there's three parts. There's the vestibule, the semicircular canals, and the cochlea. Cochlea is for hearing. Semicircular canals are for rotational movements. And the vestibule is for linear and gravity movements. So here's where we get your balance and equilibrium. And this is for hearing. And so you're going to see the cranial nerve 8 is the vestibular cochlear nerve, because we're looking at the vestibular complex and the cochlea for balance and equilibrium in hearing. On the outside is this bony structure. So this brown stuff is bone. So this is all bone on the outside. So bone. Blue is membrane on the inside. Then there's fluid as well. So you have perilymph fluid surrounding the membranous labyrinth, and inside the membranous you have endolymph fluid. So there's bone and fluid. Let me take it back a minute. When you're looking at it like this, these are the semicircular canals and the vestibule, and this is the cochlea. This right here is the round window. The round window, it's just really a window that is open into the cochlea for the vibratory energy to enter the cochlea to actually move the fluid in the cochlea. So when I'm talking about perilymph fluid, that vibratory energy is going to actually create a wave of perilymph fluid in the cochlea. And so that perilymph fluid is here in the scala vestibuli. It's the upper part. And also perilymph fluid in the scala tympani. And then you're going to have endolymph fluid inside the membranous part. So there's different fluids going on. So you're going to see the scala media, that's with endolymph. So let me see if I can highlight that. And then the scala vestibulia is perilymph and perilymph. What you're looking at is if we were to cut straight through the cochlea and then we were to look at it, like open it up and look at it, that view, we're now seeing this is the upper part, this is the membranous part in the middle, and that's the lower part. That's important to understand because the scala vestibuli abuts the oval window, and the vibrations of the auditory ossicles go through the round window and move the perilymph fluid in the scala vestibuli. So it's moving fluid. And so if you're looking at it here, sound waves are coming in. It's going to hit the tympanic membrane, and those sound waves are going to then become vibrations. And so these vibrations, you're going to vibrate the malleus, which then vibrates the incus, which then vibrates the stapes. And that vibratory energy enters the oval window. And here is where the vibrations create a wave of perilymph fluid. And so a wave is being created, and that wave, when it comes crashing down, is going to then deflect this membrane. And it's going to ultimately mechanically bend these receptors that then can generate an action potential because they're mechanically gated. And so they are mechanical receptors or mechanoreceptors. This membrane right here that we're seeing, this is deflecting down with the wave crashing, right? Whatever that sound wave is, wherever it landed. And it's going to then bend what's called the tectoral membrane. And these little hairs that are embedded in that tectoral membrane are going to be bent when it pushes down on it. And they're going to mechanically open up potassium channels, which will then depolarize and create an action potential. That's if that sound wave hits in the right spot. If we don't have that pitch, we don't have receptors for that particular pitch, it's too high of a pitch, that energy just goes through and comes out the round window. So this is for pitch of sound waves we do not have receptors for. We can't hear a dog whistle. The pitch is too high. We don't have receptors for it. Energy, it still vibrates the tympanic membrane, which vibrate the auditory ossicles, which move the perilymph fluid, but it goes all the way to the tip, which is called the helicotrenma, and then it's going to come on back through the scala tympani, and that fluid's moving through the scala tympani, and that fluid energy is just going to then leave the round window, never having pushed on any hair receptors and never generating any action potentials. So we have no awareness that there was that sound wave out in the atmosphere. So the nature of waves or sound waves is that there's an amplitude and a frequency. The amplitude is the height, and the frequency is, like how many in a period of time. So the amplitude or the height is due to loudness. The louder the sound, the bigger the amplitude or the bigger the height of the wave. And so it's going to be more dense, it's going to have more energy, and it's going to result in more energy, so more vibratory energy, which is going to basically create a tsunami. And I don't even know how to spell tsunami, but it's going to create a tsunami wave of perilymph fluid. And if you think about it, that tsunami wave, if you're listening to loud sounds, that tsunami wave is really pushing down and really going to bend these hairs, and it can break the hairs. So that's how we lose hearing ability with loud sounds, is that we just create with these loud noises over and over and over again, we have so much vibratory energy, we just have giant waves crashing down on the tectoral membrane and really bending those hair receptors over and over and over again until they break. So that's loudness. That's the amplitude. Pitch is the frequency, and frequency or number of sound waves per second. And so that's what hertz are, right? So if we have a high pitch, it means that there are lots of waves in 0.5 seconds versus lower pitch are fewer waves. And so these sound waves, when they get transferred into the cochlea, are going to be like rolling hills if it's a low pitch sound. Those waves are gonna take a lot longer. They're gonna travel a lot longer before they come down and push the tectoral membrane. So low pitch sounds are going to be, they're going to hit receptors farther away from the round window because they're just longer before they crash down. Whereas high pitch, they go up and they come down. So they're gonna hit receptors near the oval window. And if you have loud, high-pitched sounds, that pretty much knocks out high-pitched sounds early. So we tend to lose our high-pitch ability to hear high-pitched sounds sooner than low pitch because they are closer to the oval window. So sound amplification in the middle ear just means the energy that is created by the waves hitting the tympanic membrane. It's gonna vibrate the malleus first, and then it intensifies with the incus, and then intensifies again with the stapedius. And so um, the auditory oscilles are said to amplify the vibratory energy. The sound waves create so much energy, but then that energy actually increases with each auditory oscill. So it's an amplification. And so that energy increases from tympanic membrane to oval window. So oval window is smaller also than the tympanic membrane, and that also is going to amplify or increase energy. So there's amplification from the tympanic membrane. It increases with each auditory oscill, and then that oval window is also smaller. So it gets even like more energy because it's going from big kind of shoved into small, and so it intensifies that energy as it enters the round window. Signal transduction for sound, which is conversion of sound energy or wave energy into action potentials, is occurring in the cochlea of the inner ear. So there's something called the organ of Corti. And the organ of Corti is, if we are looking at this, we have the tectoral membrane, which is here. This is the tectoral membrane. I'm drawing it in black. And again, you're going to have the vestibular membrane on top. So the fluid's going to move, right, with the sound waves. And it can push down on the vestibular membrane, which then pushes down on the tectoral membrane. So this is the tectoral membrane. The organ of Corti are where you have these little inner hair cells embedded in the tectoral membrane. And then you have the outer hair cells, which then have the axons which are going to become the cochlear nerve. So all of these little hair receptors are going to have the outer hair cells have axons that become the part of the vestibular cochlear nerve. And that complex is called the organ of Corti. And so the hair cells of the organ Corti, they are the receptors for sound. They're on top of the basilar membrane. They have the tectoral membrane on top of them. And so they're said to be embedded in the tectoral membrane, and they're oriented from short to tall. So there's different sizes. So that's the organ of Corti. Now, you have sound waves in the external auditory canal. They hit the tympanic membrane. It vibrates the malleus, vibrates the incus, getting more intense with each auditory oscule, and then goes into the oval window and causes a wave. Very limp wave. Depending on the pitch, this is going to be high pitch. These are going to be lower pitch. Those waves go farther. Let's look at the high pitch wave. It hits the membrane, vestibular membrane, and that membrane is going to bend the tectoral membrane. As it bends these little hair receptors, they are mechanoreceptors. It has a very, 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 endolymph has a really, 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 really high concentration of potassium outside. And so it works a little differently in that the bending of the little hairs, they have mechanically gated potassium channels at the ends of each hair. And as they're bent, it mechanically opens potassium channels. So if you bend in the direction of the tall hair or stereocilia, the channels are going to open. And that causes potassium to come in, and the inside gets more positive or depolarizes, which opens voltage gated calcium channels, which then can cause neurotransmitter to be released and action potential to be generated. If you bend in the opposite direction, it can hyperpolarize by closing potassium channels. So cation channels allow potassium to move through. Potassium is high in the endolymph. And so if those potassium channels open, potassium is going to come in. Increase in potassium is an increase in the voltage, right? And so that's going to lead to depolarization. How do we code for loudness? Well, it's how many action potentials are being generated. And so if it's really loud and there's a lot of energy and it stays bent and all 4 of these mechanically gated potassium channels open, there's a very high amount of potassium entered. These voltage gated calcium channels stay open for longer. There's more neurotransmitter being released, which results in more action potentials being generated. And so more action potentials being generated coming into our auditory cortex, we are going to know that it is a lot of energy and it's loud. So it's really based on the amount of deflection, how many of these mechanically gated potassium channels are open and for how long, and that results in how many action potentials generated, and that's how we perceive loudness. Pitch is just based on the location or deflection of that basilar membrane. And so again, this would be high pitch, right? They're high short waves that come crashing down real quick versus low pitch. These waves travel farther before they are going to push down. And so that's how we can tell the pitch, which receptors are being activated. So fibers near the oval window, high frequency. Fibers closer to the apex, which is called the helicotremor, are lower pitch. So sound transduction, sound waves beat the tympanic membrane. Tympanic membrane starts to vibrate and vibrates the auditory ossicles. Auditory ossicles then send that vibration into the oval window, into the cochlea, and are going to move fluid. That is perilymph fluid. As the fluid pushes down or crushes down on the vestibular membrane, it's going to push the tectoral membrane, then the tiny hair. They're going to mechanically open up. When they're bent, potassium comes in and ultimately generates an action potential. Again, this is waves being created in the perilymph of the scala vestibuli. Waves with frequencies below threshold of hearing, that is, we don't have the hearing receptors for that particular pitch. That energy goes all the way to the helica trema and then out the back and out the round window. If it is in our range, then it's going to go like we just went through. Again, in our sensory lab, we are going to look at tuning forks and hearing sensory. Conduction deafness, by the way, is where it's just like it sounds. There's something wrong with the conducting of energy. So it's blocked sound conduction to the fluids of the inner ear, to the perilymph. It can result from earwax in your external acoustic meatus or ear canal. It can be the eardrum is perforated, or you have too much mucus in the tympanic cavity in your middle ear, and so those auditory ossicles can't vibrate. The deal is with conduction deafness, you're not really effectively transferring the sound wave energy to the cochlea. So there's a breakdown in that energy transfer. That's different than sensoroneural deafness. That's where you have damage to the neural structures. Say, for example, the hair cells are damaged, or there's some structural damage to the cochlea. That's going to be sensorineural deafness. Central deafness would be you have something in your brain damage to the neural pathway. As for the vestibuli, semicircular canals, same structure. They have a bony outer labyrinth with perilymph surrounding a membranous inner labyrinth with little hair cells. The utricle is continuous, the semicircular canals. The saccule is continuous with the cochlear duct. The saccule and utricle are both for gravity and linear acceleration. These sacs house receptors that respond to motion or changes of head position. So the semicircular canals, you have three. You have an anterior canal, a lateral canal, and a posterior canal. There is fluid in here. So again, you're going to have perilymph fluid and endolymph fluid. And the fluid, by the way, can travel that direction, the semicircular canal, or that direction, or it can go this direction, or it can go this direction, right? Or this direction, or this direction. So the direction of the fluid moving in these semicircular canals allows your brain to understand that you're rotating to your right or you're rotating to your left. That would be the lateral, right? These are for rotation, right or left. Posterior would be side to side. So if you're doing a cartwheel to the right or left. And then anterior would be doing a somersault forward or back. And so again, you have fluid in here, and this is inside the membranous. You have endolymph in there, and then you have what's called the cupula, and inside you have the little hair receptors here. And again, they're mechanically gated, and it's just going to depend if the fluid is pushing the hair receptors that way versus pushing the hair receptors that way. So the rotation, when the head begins to rotate, the bony outer portion rotates with it in the perilymph, and then the inner membranous and the endolymph are all rotating. And the endolymph, though, lags behind the motion of the head. And so fluid force on the cupula causes the hairs to bend, and thus causing the mechanically gated potassium channels to open and cause depolarization. So you're rotating your head, and it's moving these little hair receptors. And every time they're bending, they're keeping their potassium channels open, and it's going to depolarize and generate an action potential. Well, you can stop the bony part by stopping the rotation, but the endolymph inside is still moving. And so you still have a feeling that you're rotating, even though you're not rotating anymore. So that's really what dizzy is, right? The fluid is still moving, even though you've stopped moving. The utricle and saccule, similar in that you have hair receptors, but they're embedded in this gel. So there's this gelatinous gel, and then on top, you have crystals called otolith crystals. And so these hair receptors are located in the gelatinous material and covered with the otoliths. And as you move, say you start to move forward, the gel is dragging the hair receptors back with those crystals. And so you can feel that your body's moving forward and the gel is lagging and dragging those hair receptors back. So that would be an example of forward acceleration. Backwards acceleration, you stop really abruptly, but that gel and otolith crystals are still moving forward. And so you can feel like, whoa. As far as gravity and linear acceleration, those hair receptors can get jammed up into the otolith crystals when you are going up. When you are dropping suddenly, you can actually separate the crystals from the gel, and that gives you that feeling of your stomach dropping out. Then the crystals come back, rest on the gel, and begin to start feeling normal again. As far as taste buds, tongue, roof of the mouth, pharynx, you have to have saliva to dissolve the chemicals in the food you eat. The chemicals that are dissolved, you have protons, and this is the acidity of what's in your food. Sodium is going to be for salt, sodium chloride. Sweet, due to protein ligands. Bitter is also protein ligands. So these different solutes are being dissolved in saliva, which is the solute is the solution, sorry, the solvent of the solution. And you have different receptors that are responding to each one of these. So some receptors respond to acid, some respond to salt, some respond to ligands that are sweet, and some respond to ligands that are bitter. And we have more receptors for sweet. Shocking, right? That's why we love sweet. We have a lot of receptors. We get a lot of response from eating those foods. Salty and sour. So we tend to like those as well. Bitter is kind of danger. And so we have some of those just to let us know, maybe you shouldn't eat that. Olfaction. We have receptors embedded in the olfactory epithelium, and also these are also chemoreceptors. So taste and smell are chemoreceptors. We need to dissolve the chemicals in fluid in order for these receptors to activate. So olfaction or smell depends on the chemicals in the air that are going to bind to those chemoreceptors in the olfactory epithelium. And this goes through the olfactory pathway. And that is going to wrap up our sensory.